In this session, we are going to focus our discussion on distributions, more specifically on the standard distributions that you've been hearing about, that we've been applying to real life situations, and perhaps you've been encountering in your exercises and exam questions. So what are distributions? We want to first look at the sort of reason why we are looking at them with such earnesty. And we want to understand what are these, how do we describe distributions, why do we use them, what properties do they have, and then we will look at two big classes of distributions: the discrete probability distributions and the continuous probability distributions. We are primarily looking at standard distributions, distributions whose mathematical properties are well known, well studied, and in other words, totally understood. All right, you can point at anywhere in the graph of the distributions of these standard distributions, and we'll be able to completely understand and predict the behavior. Now, if we have completely understood everything, what's the use of it, right? There's no more challenge, no more mystery. But the the benefit, however, is now in the applications to real life situations. So why standard distributions? In what is going to follow, whenever we talk about distributions, unless otherwise stated, it will be all about the standard distributions. So what are standard distributions? You have kind of seen it in the agenda. They include things like Bernoulli distribution, binomial distribution, Poisson distribution, normal distributions, right? So these are all called standard distributions because, number one, they are known completely mathematically. It may be complicated, you might not like the taste of it, but as far as mankind is concerned, we know it completely, right? We can draw a graph, we can plot it, we can find the average, we can know the variance right there. You don't have to do experiments. That's the main benefits in connection to reality, right? So mathematically, they are kind of not very interesting in that we have studied everything there is to know about it. But when we apply to real life situations where, as you might know, a lot of things are not known or else will be costly in terms of time or money or resources to measure, to count, to investigate and survey. So that link now is that can we put them together, right? Can we use appropriately chosen standard distribution as if they actually describe the real life situation that we are encountering? Okay, so that's the main beneficial application that we like about standard distributions. So they're completely known, and if we can establish that link between this unknown reality, what are the probabilities of this and that happening, right? We would like to make a very judicious decision on it, but we don't know the reality unless we do expensive and kind of after the fact measurements. Well, if we can establish the link to one or even a few well-known standard distributions, then if we pretend that they are one and the same, the well-known, well-studied behaviors in the standard distributions will be giving us all the probability calculations and mean and variance and everything as if they actually describe the real life situation. All right, so that's the nice thing about standard distributions being known. And if to the extent that they can actually describe very well, maybe not perfect, but very well, the actual real life situations, and maybe not completely for all possible cases, but substantially for maybe 90% if you're lucky, or better still, 95%, or if you're unlucky, maybe 80% of the situations. That's still not bad, right? And if that's the case, mathematical analysis will give us insights into reality. For example, if we don't know about income distribution of a population, but we say, let's say that follows normal distribution. Now, truth be told, most income distributions will not follow normal distributions. because it'll be symmetrical, right? So it will not be the right choice. But for simplicity, suppose we assume that it follows normal distribution of certain mean and standard deviation. Then we say, oh, well, what's the proportion of population getting 100,000 and more per year? And then we can calculate that area of the normal bell curve. And that's easy, even though it's complicated mathematically. We can use packages and software to calculate that proportion on the graph, and then we can gain some initial estimates. Maybe it's not accurate, but it's not far wrong, right? It's order of magnitude accurate. And in some cases of planning and estimations and ballpark discussions, initial plans, for example, that's often good enough. So that provides insights into actual situations. And modeling, right? So I've been actually already using this benefit in that real life measurements often are quite expensive and time consuming. So, and sometimes not even possible, even if you have the time and the resources. So using a model as a rough estimation, right, and it may be actually quite accurate even, then we are pretty lucky. Then it will provide a lot of benefits in terms of knowing completely about the population behavior. For example, income. For example, accident rates on highways. For example, duration of travel trips. All these are very interesting measurements that are important to the relevant industries, the travel industries, the medical industries, the logistics industries, the automobile industries, and so on. So various population of measurements, member population, those are all bag of data, right? Bag of measurements. They can be quickly, immediately, and accurately even modeled by standard distributions. Another benefit is in terms of approximation. Fair enough. Sometimes real life measurements get complicated. So we don't even understand the science behind it. We can only record the phenomena, and we don't really have the ability to yet explain what's going on. For example, COVID-19 gives us a very modern example of what confounds human knowledge, right? The frontiers of human knowledge. We have no idea how this virus behaves. What is the half-life, for example? How long does the virus live? Is it very lethal? Does it cause death? How long does it cause death? Does it cause a painful death or immediate death? How can we prevent it? And so on and so forth. There are a lot of measurements that are important, but not possible to get, too complicated to get, takes a long time to get, very expensive to get, takes human lives to get, etc., etc. So even if we desire perfect modeling, sometimes, oftentimes, more often than not, it is enough to get a rough approximation. So, for example, if we say, well, the virus has a lifespan of about 7 days, plus minus 1-2 days, I guess. So if that's the initial estimate that scientists get, maybe the first month of the pandemic, the pre-pandemic, right? We didn't even know it was pandemic. Well, perhaps you can say, suppose the lifespan of the COVID-19 virus follows normal distribution. Suppose, right? So we can approximate until further evidence corrects our supposition. So we have a working model to work with. And that model, just like 3D model, may not be perfect. Nevertheless, it provides a very concrete item, a description there for us to nudge a little bit, correct a little bit, twist a little bit there, with further evidential corrections. So approximations can be readily done because we have a whole pool of standard distributions to apply to various situations. So not bad. It's like Lego block, right? Individually, the bricks don't look like anything that we like to describe, but they are there. So we can always try to stack them up and apply them so that they form into a shape that roughly looks like a dinosaur if we are describing a dinosaur. So approximation power is there if we use the standard distributions. And the last point, I think, is nice because just like the COVID-19 pandemic, we have no idea, none at all, no measurement. Imagine the day one of pandemic, right? We have no data on the desired measurement at all, such as answering this very question: how long does the virus live, right? So if we have no idea at all, we might not be able to assume any distribution. So we even have a distribution to talk about no distribution, no idea this situation. We can use the uniform distribution, like every number is possible, because if you debate scientist to scientist, data analytics professional to data analytics professional, it might be just the best model when you say we all have no idea, so all numbers are possible. So it's a uniform distribution from 3 days to 14 days. We have no idea. Yeah, because until further evidence arises, we cannot argue for shorter or longer lifespan of the virus. So that allows us to bootstrap. Yeah, we know it's not negative. We know it's not zero, and we know it's not infinity number of days either, right? So where is it? And so we can begin to narrow with certain heuristics, domain expertise, virus experts who kind of understood all but COVID-19 in the special case. So they know most viruses don't live beyond 30 days. Example, I don't know, right? So if that's their expertise, their industry medical insights, then we can say, well, it's a random number from 3 days to 30 days. So by using standard distributions, we have the ability to start this modeling process, right? Rather than saying, well, we have to have somebody die first and then we can measure, right? We have to have somebody getting into serious illness first before we can even think about modeling. So you see, this is kind of a very inconspicuous step, but it's very, very important, right? Without measurements at all, we can already start this bootstrapping process. We can already start modeling mathematically the probability distributions of these measurements. So that's why we like standard distributions a lot. That's why we really have to master them. Okay, so that there's a whole suite of, I don't know, maybe hundreds or several hundreds of standard distributions, classes of distributions. Each distribution, like uniform distribution, actually covers a whole infinite number of related uniform distributions, right? Because you can say uniform distribution from 0 to 6, 1 to 5, 1 to 10, 1 to 15, right? And then 10 to 20, and so on. So it's actually infinite number of items in each class of distributions. And if you Wikipedia around, it's easy to find hundreds of such classes of distribution. So bell curve is one class because we have many, many normal distributions of different means and standard deviations, right? So we have a lot of ability to jumpstart right away and benefits from all these properties that standard distributions give us.